Hi everyone, we are Group 17, and our project is about implementation of triangle counting algorithm. This is our outline, and let me show you the first part, introduction. Graphs as a data structure can clearly reveal the associations between data and are often used in complex modeling, such as data modeling in information systems. And nowadays, graph computing is commonly used for analyzing and processing huge amounts of graphical data generated by social media users to uncover hidden important information and serve the target users of business applications. Triangle counting as a local topology counting method has been widely applied in the field of web science with the development of large-scale graph modeling, index databases, and network fraud detection. There are three main applications of triangle counting, including social network analysis, graph processing, and bioinformatics. But most related algorithms currently require the input of the entire graph to get a result. And with the explosive growth of data size, large graph data often contains tens of millions of vertices and edges, which makes it difficult to store the data completely in memory and make the model return the computation results in real time. Therefore, in this project, we use the basic principle of triangle to analyze and implement the Tetris algorithm to estimate the number of triangles when the complete graph could not be accessed. The method we use, created by Barrow and Sacchetti, 2020, is to get only part of the graph information by using an epsilon delta estimator, which is a randomized algorithm. And for related work, at present, many triangle counting algorithms are based on arboricity and subgraph listing algorithms of Chiba and Nishizaki, 1985. We draw on some of the concepts about the random walk from this. And the Tetris algorithm used the idea of two-stage sampling from Eden et al. 2017-2020 to simulate the generation of age samples in accordance with the degree distribution based on age. Besides, Dasgupta et al. 2014 firstly formalized random walk access model based on the estimation of average degree. And Cherichetti et al. 2016 gave an elegant algorithm for sampling a uniform random vertex. In addition, the collision-based age estimator in algorithm 2 is based on a result of Ruan and Suo, 2016, and Rochman et al. 2014 provided vertex MCMC algorithm for performance comparison with Tetris algorithm.
Hello, I'm Wulong Zhao. Now let me introduce the algorithm we used in our project. Firstly, I need to talk about some variable definition for the algorithm. We define the graph as G, the vertex R, and the edge E, and the names stand for the size of vector and edges. For each vertex, we define the neighbor points as MV and degree dV. For each edges, the degree of E is defined as the minimum degree of its two vertex. For each triangle in the graph, we define it as V1, V2, V3 using the lexicographic ordering and each degree descending ordering. And TE is stand for the number of triangles related to an edge E. Before introducing the main algorithm, I will introduce the random walk access model. This algorithm starts with an arbitrary vector, making queries to find more vertices. There are three types of queries. Random neighbor query is to get a uniform random neighbor of a vector. Degree query is to get the degree of a vector. As for edge query, it judges whether the edge between two vertices is present in the graph. The algorithm makes queries from the original vector to achieve new vertices, then make queries from the new vertex to discover more. Now, let me introduce the main algorithm. The first one is the triangle counting algorithm. To start the algorithm, Some parameters are required: the length of random walk, the number of subsample, and the mixing time. The algorithm starts with an arbitrary vertex R. After a random walk of length R, it gets a collect of edges in a set R, and computes the degree of all edges. After that, all edges are sampled with a probability proportional to the degree. For an edge E sampled from the last step, the algorithm makes a uniform random sample to get a neighbor W from an E. After that, the algorithm checks whether a triangle is created by EW. If yes, then it checks whether the triangle is uniquely assigned to the edge E. Finally, the algorithm requires the number of edges and computes the number of triangles. The second one is the edge count estimator. It uses the edge set and the estimate mixing time to estimate the edge number of the whole graph.
This part is the theoretical analysis of the algorithm. In this part, we want to show that this algorithm enables us to get the estimator satisfying the target. And there are two steps. First, showing some edge selection with some good properties will provide us with accurate estimator, and then prove that we perhaps will get the good set of the edges with this algorithm. For a fixed edge set R, we denote the variable y in the turn step in the algorithm as yr, and we know that y is the average value of the yi's in the algorithm. Therefore, we have the following properties for the variable yr, whose expectation is TR over dr. And with TR over dr, we can compute the correct count of triangles. And the second equation shows us that with high probability, yr is around its expectation TR over dr tightly. Next is a definition of the good set, which we mentioned before, and it will be used later. If an edge collection have these two properties, the set will be called good. Then we can prove that the estimator XR is accurate conditioned on R being good as the lemma. It can be easily proved with the range of Y from the lemma 4.2, the range of M bar from the edge counting algorithm, and the second property of the good edge set. You can see that the variable M bar, dr, tr can be cancelled, and only t remains, and the lemma is proved. This is the last part, and it is to show that the edge selected in the algorithm has these two properties. The lemma is shown and proved in the paper, with the probability at least 1 minus 1 over 4 log n. TR over dr can be computed, and it is clear that the first property is followed. And with the third item in the lemma, we know that it perhaps will also follow the second property with the probability. Therefore, we may get a good set which satisfies the aim of the task with our algorithm.
Hello everyone, this is Hu Songyuan. The previous member introduced the principle of model reuse. Because the following experiments will involve the comparison of results of the multiple models, here I will briefly introduce the principles of other models in the experiment. First is the vertex MCMC model. The sampling process starts from an arbitrary seed vertex U. Then you will choose one of the neighbors of U using algorithm 2, which is simply an implementation of Metropolis Hastings algorithm. Once a vertex is selected, vertex MCMC will compute the cumulative mass function of multinomial distribution and uses the direct sampling method to sample a triple. The process continues until the desired number of triples the parameter k, are obtained. For this whole process, at each step of the random work, two members of the current vertex are sampled uniform at random and tested for the existence of a triangle. Next is the SRW model. The core idea is to collect k-node graphlet samples through L consecutive steps of the random work. Specifically, for each state xi of the random work on GD, it keeps the history of the previously visited states, then considers the subgraph induced by nodes contained in XL as a k-node graphlet sample. If the consecutive L steps on GD fail to collect k distinct nodes in V, it just continues the random work until it finds L consecutive steps which contain k distinct nodes. For this whole process, every 3 consecutive vertices on the random work are tested for the existence of a triangle. Then is the SERWC model. It first samples a vertex U uniformly in the vertex sampling algorithm. Then it uniformly samples a vertex V neighboring to U and checks whether it is also a neighbor of the other. After that, it picks one of the neighbors of U or V and checks whether it is also a neighbor of the other. If the answer is yes, we have found a triangle. Finally, proper scaling has to be done to turn this into an unbiased estimator of the triangle count. Finally, I give the comparison of these models' principles. All these 4 models use random work to reduce the computational complexity. The difference of their accuracy may be the difference of their judgment principle. After that, my team members will introduce the experimental comparison results of these models.
And then I'll introduce some experiments we've done. We choose 10 different graphs and compare the results of 4 different algorithms. First, let me introduce our dataset. We choose 10 graphs with different size of vertices and edges, and then calculate the exact number of triangles of them. The information of them is listed as following. The sparsity of triangles is the number of triangles divided by number of edges. For example, for the first graph, the sparsity of triangle is 7.8k divided by 24.2 m. Okay, then I will introduce the parameters. We compared 4 algorithms. They are Tetris, Vertex MCMC, SRW1, and SCRWC. For each algorithm, we use the same parameters. We set L as 0.05 R. L makes to 25, and we try different R. Well, in this code, R is set to a probability times the number of edges. And we use 6 different probabilities to achieve different R. There is a picture of config file. You can see we need to set input file path, number of repeats, algorithm name, and so on. Number of repeats means how many times we apply for one algorithm. For example, when this set to 10, we run Tetris for 10 times, and we take the median error as our estimation error of this algorithm. The result is shown as the following figure. We can notice that in most cases, Tetris can get a pretty good estimation with low percentage of queries compared with other algorithms. And with larger R, in other words, percentage of queries in this figure, the estimation is more accurate. We can guess from the experiment result that for some graph whose triangle is too sparse or too few, all algorithms can perform very well by seeing a small part of whole graph, such as the results of IMDb in Asia, in Europe, and so on. For the graphs that have two dense triangles, this algorithm can give an accurate estimation error, such as Webin-China. Also, with the increasing of length of random walk R, the median error is getting smaller.
Next part, let me introduce the real performance on almost all datasets that the Church's algorithm has. I will introduce 4 additional experiments which suggest the high accuracy and robustness of Church's. And first of all, we apply the Church's to 4 big datasets, and we fix that Church's can only query 3% of the ages and calculate the average relative error percentage and the variance error in the estimation. We can see the figure below shows the average relative error percentage of Church's in 4 big datasets. We can see the Church's achieved a median error of up to 3% for each dataset, and the variance of estimation is also very low. Okay, in the second experiment, we increase the length of random walk R. The average relative error percentage of Church's is shown in the figure below. On the y-axis, we can see median relative error percentage, and on the x-axis, we have percentage of the ages visited. For larger datasets, the Church's algorithm achieves 2% accuracy with only 2% age access. The figure below shows the convergence of Church's based on Weibo and Twitter dataset. The final output of Church's is drawn on the y-axis, and every 100 rows corresponds to a fixed value of R. On the x-axis, we increase R to show the percentage of queries made by Church's during execution. The maximum query percentage corresponding to the maximum setting of R is 3%. And based on the Twitter dataset, 4 vertices are randomly selected from each degree-based vertex bucket. On the y-axis, we give the average relative error of 100 rounds of Church's with the corresponding vertex as the seed vertex. In the figure below, the accuracy of Church's is not affected by seed vertex selection, which shows the robustness of Church's algorithm to seed vertex selection.